A low hum echoes across the cosmos, the recorded sound of a black hole. These cosmic giants are not the simple voids we once imagined. They are the key to unlocking the universe's most profound secrets. By the end of this journey, you will explore 25 mind-bending theories that could redefine reality itself. We will venture to the very edge of known physics, where singularities might birth new universes and information is stored on a two-dimensional boundary. What one mystery about black holes has always captivated your imagination? That recorded hum is a constant reminder of their activity. But what if these cosmic giants are not the perfect traps we once believed? The first theory shatters that very illusion. Stephen Hawking proposed a revolutionary idea that black holes are not actually black. They possess a faint, almost imperceptible glow. This phenomenon, now known as Hawking radiation, arises from the chaotic quantum sea that exists everywhere, even in the vacuum of space. Pairs of particles and their anti-particle counterparts constantly flicker in and out of existence. Normally, they annihilate each other almost instantly, but at the very precipice of a black hole's event horizon, a strange theft can occur. One particle falls inward, past the point of no return, while its partner escapes into the cosmos. The energy for this miraculous escape is stolen from the black hole's own gravitational field. This process causes the black hole to very slowly lose mass, evaporating over unimaginable eons. It means that black holes have a lifespan and a theoretical end. The search for this faint whisper of radiation is one of the most important quests in modern physics. Detecting it would be our first direct glimpse into the mysterious union of gravity and quantum mechanics. If we could confirm Hawking's brilliant prediction, we would finally have a key to a theory of everything. This leads us to a startling paradox tied directly to this evaporation. What happens to all the information about the stars and matter that fell in? Does it simply vanish from our universe, violating a fundamental law of physics? That slow evaporation forces us to confront a deep cosmic law. Nothing, not even the information describing a fallen star, is truly lost. This is the information paradox, a puzzle that threatens the very foundation of physics. Yet the mathematics that describes black holes holds a strange and beautiful symmetry, one that suggests a possible solution. The equations allow for the existence of a perfect opposite, a white hole. If a black hole is a cosmic drain from which nothing can return, a white hole is a cosmic fountain from which nothing can enter. It is a region of spacetime that violently expels matter and light, forever pushing everything away from its core. You could not enter a white hole even if you tried. Its event horizon is an impenetrable barrier, a one-way exit door for the universe. The idea emerges from the same elegant equations of general relativity that predicted black holes in the first place. They are mathematically possible, a mirror image of the darkness we are familiar with. So where are they? One compelling thought is that every black hole might be connected to a white hole through a tunnel in spacetime, a wormhole. The matter swallowed by the black hole could be hurled out through its white hole counterpart, perhaps into an entirely different universe or a distant part of our own. In this view, a black hole is not a final grave but a gateway. Another possibility is that the Big Bang itself was the ultimate white hole event, a singular outburst of all the energy and matter we see today. While we have yet to observe one, the search continues. Some astronomers scrutinize unusual cosmic explosions, immense bursts of energy that seem to come from nowhere, wondering if they are witnessing the brief, brilliant death throes of a white hole. The existence of these cosmic fountains would rewrite our story of the cosmos, suggesting that for every ending, there is a beginning waiting on the other side. This idea of a gateway naturally leads to one of the most thrilling concepts in all of physics. Black holes might not be cosmic dead ends, but rather the entrances to tunnels through the fabric of reality itself. These theoretical passages are known as wormholes, or more formally, Einstein-Rosen bridges. They emerge as valid, though highly unstable, solutions to the equations of general relativity. Imagine the universe as a vast sheet of paper. To get from one distant point to another, you would normally have to travel all the way across the surface. But if you could fold that paper, bringing those 2 points together, a wormhole would be a tiny bridge piercing through the gap, a cosmic shortcut eliminating the need for the long journey. The immense gravitational force of a black hole could, in theory, provide the necessary warping of spacetime to create and hold open one end of such a tunnel. The other end could be connected to a white hole, spewing everything out somewhere else entirely. This somewhere else could be another galaxy, a different time, or even a separate universe. But here lies the challenge of traversability. The gateway is thought to be incredibly unstable. The moment even a single particle tries to pass through, the tunnel would likely collapse into a singularity in a fraction of a second, crushing anything inside. Furthermore, the region at the very center, the throat of the wormhole, would be flooded with intensely energetic radiation that would vaporize any matter instantly. To make such a bridge passable, you would need a form of exotic matter with negative energy density to prop the throat open, counteracting the immense gravitational forces trying to slam it shut. While we have no evidence such matter exists, its theoretical possibility is what keeps the dream of wormhole travel alive in the minds of physicists. This concept also opens a profound door to the possibility of time travel. If one end of the wormhole could be moved at a significant fraction of light speed, time would slow down for that end relative to the stationary end, as predicted by special relativity. You would then have 2 connected points in space that are also 2 different points in time. Walking through one way, you might travel into the future. Walking through the other, you could step into the past. This is not just science fiction, but a genuine consequence of combining our best theories of gravity and motion. The search for stable, traversable wormholes remains one of the most exciting frontiers in theoretical physics, a quest to find the universe's hidden subway system. The gateway of a wormhole presents a profound puzzle about the very nature of space. What is it made of, and how much information can it truly hold? The answer might be the most radical idea in all of physics. Our universe, with all its stars, planets, and seemingly solid 3-dimensional depth, could be a hologram. This is not a suggestion that we are living in a simulation created by advanced beings. The holographic principle is a serious scientific theory that emerges directly from the heart of a black hole. It begins with the information paradox. We know that information cannot be destroyed, yet a black hole that evaporates via Hawking radiation appears to erase every trace of what fell in. Where did the information go? The startling solution proposed by physicists like Gerard T. Hooft and Leonard Susskind is that the information never actually falls into the black hole at all. Instead, it is perfectly encoded like a cosmic blueprint on the 2-dimensional surface of the event horizon. Every particle, every atom, every characteristic of a star that crosses that threshold is translated into incredibly tiny vibrations or bits of information on the boundary membrane. The 3-dimensional interior we imagine is just a projection of that data, much like a 3-dimensional movie is projected from a 2-dimensional film. The black hole's entire contents are painted onto its surface. This principle does not stop at the edge of a black hole. Theoretical physics suggests it might apply to the entire cosmos. The space around you, the room you are in, everything you see and touch, could be a holographic projection from a vast, distant, 2-dimensional surface at the edge of the observable universe. We are not seeing the real code, we are experiencing the projection. This means our perception of a 3-dimensional reality is a magnificent illusion, a depth that emerges from a fundamentally flat reality. If this is true, it redefines the very fabric of existence, suggesting that the universe is not what it appears to be, but something far stranger and more interconnected. The holographic universe is a breathtaking concept, yet it leaves us with another, more tangible cosmic mystery. All the galaxies we observe are held together by an invisible gravitational glue, a substance we call dark matter. We can see its effects, but we have never directly detected what it is made of. One of the most compelling theories suggests the answer has been hiding in plain sight, within the very objects we have been studying. Primordial black holes could be the universe's hidden dark matter factories. These are not the stellar mass black holes born from dying stars. These would be ancient relics forged in the extreme density and pressure of the universe's first moments after the Big Bang. Cosmological imperfections, tiny pockets of space that collapsed under their own immense gravity, could have created black holes of almost any size, from smaller than an atom to larger than a star. The most promising candidates for dark matter are thought to be asteroid-sized, with masses comparable to a large mountain, or planet-sized, far more massive than any rock in our solar system. Their small size and lack of light emission make them virtually undetectable by conventional telescopes, a perfect description for the unseen matter that binds galaxies. The search for these ancient ghosts is underway. Astronomers use a technique called gravitational microlensing. When one of these primordial black holes passes in front of a distant star, its gravity acts as a lens, bending the starlight and causing the star to temporarily brighten. By scanning millions of stars for these characteristic flickers, scientists are narrowing down the possible mass ranges these objects could have. Finding a population of these primordial black holes would be a monumental discovery. It would solve two profound puzzles at once, revealing the nature of dark matter and providing a direct window into the violent conditions of the infant cosmos. The invisible hand shaping the universe might not be a sea of exotic particles, but a vast swarm of ancient black holes, the universe's original shadows. But the holographic principle, for all its elegance, introduces a terrifying possibility at the very threshold of a black hole. Einstein's general relativity offers a comforting prediction for anyone doomed to fall in. As you cross the event horizon, you should feel nothing at all. There is no physical barrier, no sudden jolt. It is a point of no return, not a brick wall. From your perspective, you would simply drift inward, unaware of the moment you crossed the line. Yet when we apply the rules of quantum mechanics to this scenario, the story becomes violently different. The principle of unitarity, a cornerstone of quantum theory, demands that information cannot be lost. If a black hole evaporates and disappears, the information it swallowed must somehow be preserved. The most radical way to preserve it is to never let it enter in the first place. This line of thinking gave birth to the firewall paradox. The event horizon might not be a peaceful boundary. Instead, it could be a searing wall of unimaginably high energy, a furious barrier made of particles with energies approaching infinity. Anything or anyone crossing it would be instantly incinerated into a fundamental soup of particles, their information scrambled and smeared across the surface. This firewall is a direct result of the clash between our two most powerful theories. General relativity guarantees a smooth, uneventful passage. Quantum mechanics, concerned with saving information, seems to demand a violent, destructive one. They cannot both be correct. This paradox forces physicists to confront an uncomfortable truth. Our understanding of reality is fundamentally incomplete. Either Einstein's elegant vision of spacetime breaks down at the horizon, or our quantum rules about information are flawed. The firewall is a signpost pointing to a deeper theory, one that can finally unite gravity and the quantum world. It suggests that the true nature of reality is hidden just beyond our current grasp, waiting at the edge of a paradox. That searing firewall presents a paradox so deep it demands we rethink the black hole's very simplicity. For decades, physicists have relied on the no-hair theorem, a powerful idea suggesting that black holes are the ultimate bald objects in the cosmos. This theorem states that a black hole can be completely described by just three numbers: its mass, its electric charge, and its spin. Everything else, every unique detail about the stars, planets, or gas clouds that fell in, is permanently erased. A black hole has no hair, no distinguishing features beyond those three values. It does not matter if you throw a perfect diamond or a chaotic cloud of dust into the void. The resulting black hole would be utterly identical if their mass, charge, and spin were the same. All the rich, complex information about what fell in is lost forever, shaved away by the event horizon. This elegant simplicity, however, clashes violently with the quantum law that information must be preserved. If the no-hair theorem is correct, then the information paradox is unsolvable, and our understanding of physics is fundamentally broken. But what if black holes are not so bald after all? A growing body of theoretical work suggests that black holes might, in fact, have hair. This is not literal hair, of course, but a metaphor for additional, subtle properties that could encode a history of what the black hole has consumed. These hairs would be incredibly fine quantum structures, perhaps imprinted on the event horizon itself. One possibility involves complex quantum fields that linger just outside the black hole like a faint, persistent aura. These fields would not be erased by the passage through the horizon. Instead, they could store a unique signature, a quantum fingerprint of everything that has vanished within. Another idea proposes that the very fabric of spacetime just outside the black hole becomes knotted and twisted in unique ways, creating permanent bumps or wrinkles that remember the past. Detecting this cosmic hair would be an immense challenge, as its effects would be extraordinarily subtle, perhaps only visible in the precise gravitational waves emitted when black holes collide. The ripples in spacetime from such a collision might carry a faint, complex hum, a whisper of the information stored on their surfaces, a signature of their hair. If these theories are correct, then black holes are not the simple, featureless tombs we imagined. They are complex cosmic objects, their smooth horizons etched with the faint, preserved memory of everything they have ever consumed, offering a potential escape from the information paradox without the need for a destructive firewall. This cosmic hair, a subtle memory etched in spacetime, hints that our understanding of these objects might be fundamentally flawed. What if the black holes we think we see are not black holes at all? There is a radical alternative that completely sidesteps the paradoxes of singularities and firewalls. They are called gravastars, a name derived from gravitational vacuum stars. A gravastar would look almost identical to a black hole from the outside, possessing the same immense gravitational pull. But its internal structure is where reality takes a sharp turn away from the traditional model. Instead of an infinitely dense point of no return, a gravastar is proposed to have a core not of crushed matter, but of dark energy. This is the same mysterious force driving the accelerated expansion of the universe. Inside the gravastar, this dark energy would exert a powerful negative pressure outward, a cosmic repulsive force. This outward push would perfectly balance the crushing inward force of its own immense gravity, preventing the complete collapse into a singularity. There would be no point of infinite density because the dark energy core acts as a final, stable state of matter. The event horizon, the signature feature of a black hole, would also be replaced. In its place, a gravastar would have an incredibly thin, shell-like boundary made of an exotic form of matter. This shell would be extraordinarily dense, perhaps only a few centimeters thick, but it would be a true physical surface. Nothing would ever need to fall into a gravastar because nothing could ever truly cross this boundary. Matter and energy striking this shell would be absorbed and would then slowly evaporate away as a form of radiation, similar to Hawking radiation, but without any information paradox. This elegant structure solves many theoretical headaches. There is no singularity to break the laws of physics. There is no event horizon to create a firewall paradox. Information is never lost, as it is merely transformed on the shell. The universe would not need to invent new physics to handle the center of a black hole, because the gravastar's core is a stable, albeit bizarre, configuration of known cosmic ingredients. The challenge, of course, is finding one. How could we possibly tell the difference between a classic black hole and a gravastar? The answer might lie in the way they interact with their environment. When two black holes merge, they create specific ripples in spacetime, a distinct chirp in the gravitational wave signal. A collision between two gravastars might produce a subtly different echo, a faint after vibration caused by their solid shells ringing like a cosmic bell. Astronomers are now carefully listening to these gravitational wave chirps, searching for any tiny deviation from the predictions for classic black holes. Finding such a signature would be a revolutionary discovery, proving that the darkest objects in the sky are not the bottomless pits we feared, but strange, stable stars with a core of cosmic repulsion, forever holding themselves up against their own weight. This profound warping of spacetime around a black hole does more than just trap light. It twists the very fabric of time. Deep within the mathematics describing a specific type of black hole, a rotating Kerr black hole, lies a secret passage not through space but through time itself. The equations of general relativity allow for the existence of what are known as closed time-like curves. Imagine a path through the universe that, instead of moving forward, eventually loops back to meet its own beginning. An object following this path would travel into its own past. In the turbulent region just outside the inner event horizon of a rapidly spinning Kerr black hole, the drag on spacetime is so extreme that these theoretical loops could form. The black hole's rotation twists the future and the past into a knot, creating a corridor where the direction of time itself becomes a matter of perspective. This is not a deliberate machine built with gears and levers, but a natural, if incredibly rare, feature of the cosmos predicted by our most robust theory of gravity. The concept immediately confronts us with a famous and disturbing puzzle, the grandfather paradox. What would happen if you traveled back in time and prevented your own grandfather from meeting your grandmother? The logical contradiction is paralyzing. You would never be born, and therefore could never have traveled back in time to commit the act. This paradox seems to make time travel an impossible fantasy, a violation of cause and effect that reality would never permit. Yet quantum mechanics, our most successful theory of the very small, might offer a way out. One potential resolution comes from the many worlds interpretation of quantum physics. In this view, the timeline is not a single, unchangeable thread. Every possible outcome of every event spawns a new, branching universe. If you were to step into a closed time-like curve and travel to the past, you would not be returning to your own past timeline. The moment you arrive and interact with events, you cause a split, creating a new, parallel universe that is slightly different from your original one. In this new branch, your actions might prevent your grandparents from meeting, but you would have come from a different reality where they already did. You would not erase your own history. You would simply be writing a new one in a separate book of reality. Another, perhaps even stranger, idea is that the laws of physics simply conspire to prevent paradoxes from ever occurring. Any action you take in the past that would lead to a logical contradiction becomes physically impossible. A gun might jam, a vital message might be lost. Some coincidental event would always intervene to ensure the timeline remains consistent. While we have no evidence that closed time-like curves exist in nature, their theoretical possibility forces us to confront the deepest questions about the nature of time. Is it a rigid, one-way street, or is it a more flexible landscape, with loops and branches waiting to be discovered under the most extreme gravitational conditions the universe can provide? The twisting corridors of time hint at a cosmos far more interconnected than we ever realized. Could it be that the universe we call home is itself nestled within the heart of a black hole? This is not mere speculation, but a serious cosmological theory that reimagines our cosmic origins. The Big Bang presents a profound puzzle, a moment of infinite density and temperature where the laws of physics as we know them break down. This initial singularity is eerily similar to the one predicted at the center of a black hole. What if they are the same phenomenon viewed from different sides? In this model, the Big Bang was not the absolute beginning of everything, but the violent birth of our universe from within a black hole that formed in a larger parent universe. When a star collapses in that external cosmos, forming a black hole, the incredible compression of matter and energy at its core might not culminate in a dead end. Instead, that point of collapse could rebound, sparking a new expansion, a new universe within its own self-contained spacetime. Our entire cosmos, with all its hundreds of billions of galaxies, would be the interior of that one cosmic seed. This elegantly sidesteps the problem of the initial singularity, replacing a mysterious beginning with a physical transformation, a cosmic rebirth. This idea leads to a breathtaking vision of reality, a cyclical or even fractal model of cosmic evolution. Every black hole that forms in our universe could, in its deepest interior, be birthing an entirely new cosmos, complete with its own physical laws and constants. We could be living inside one such child universe, our Big Bang simply the moment our parent black hole formed. And in turn, the black holes we observe here might each contain a fledgling reality of their own. This creates a magnificent, infinite cascade of universes within universes, a cosmic matryoshka doll of existence. It even offers a potential explanation for why our universe seems so finely tuned for life. The physical constants we take for granted, like the strength of gravity or the mass of a proton, might not be fundamental. They could simply be inherited parameters, the unique characteristics of our particular parent black hole. In another universe, born from a different black hole, the laws of physics could be completely alien. While this theory is incredibly difficult to test, it provides a powerful narrative that connects the very large to the very small, suggesting that the key to understanding our own cosmic home lies in the mysterious nature of the black holes that dot its sky. This cosmic nesting doll of universes forces us to ask what truly lies at the center. String theory, a leading candidate for a theory of everything, offers a radical answer that banishes the troublesome singularity forever. It proposes that the heart of a black hole is not a point of infinite density, but a fuzzball. Imagine the fundamental threads of reality, the vibrating strings that string theory posits as the building blocks of all matter, becoming wildly tangled and swollen. They would expand to fill the entire volume inside the event horizon, forming a giant, fuzzy ball of cosmic yarn with a definite, finite size. There is no sharp boundary, no empty space inside, just a dense, fuzzy surface that extends all the way to the core. This single idea solves multiple profound problems in one elegant stroke. Because the fuzzball has a defined structure, there is no singularity where the laws of physics break down. The nightmare of infinite density simply vanishes. Furthermore, the complex, tangled nature of the strings provides a perfect natural mechanism for storing information. Every unique configuration of the strings, every twist and vibration, can encode the history of what fell into the black hole. When the black hole evaporates via Hawking radiation, this information can be faithfully returned to the universe as the fuzzball unravels. The information paradox, the central crisis of modern physics, finds a potential resolution not on a holographic screen, but within the intricate, fuzzy depths of the black hole itself. This makes the black hole a fundamentally quantum object from its very core to its surface. While the mathematics of fuzzballs is incredibly complex and remains theoretical, the concept provides a compelling vision, replacing the terrifying void of a singularity with a tangible, if bizarre, object that obeys the known laws of physics. It suggests that the universe's most extreme environments are not places where science ends, but where it reveals a deeper, more intricate layer of reality. That intricate fuzzball of strings represents one possible fate for collapsed matter, but nature may have an even stranger outcome in store. Between the known extremes of neutron stars and black holes lies a theoretical no man's land, a mysterious mass gap where the rules seem to blur. We know that when a massive star dies, its core collapses. If the remaining core is between about 2.5 and 5 times the mass of our Sun, it typically forms an incredibly dense neutron star. If the core is heavier than that, it is thought to collapse directly into a black hole. But what happens to objects that fall right in the middle? This is the mass gap, and within it, a bizarre hybrid object might be possible, a black hole neutron star. Imagine a neutron star already so dense that a single teaspoon of its material would weigh billions of tons, continuing to collapse under its own immense gravity. It has passed the point where neutron pressure can support it, but it has not yet crushed itself into a full black hole. In this transitional state, the matter would be in an unknown, hyper-compressed form, perhaps a soup of even more fundamental particles like quarks. It would possess an event horizon, trapping light, but its core might still be a seething, turbulent ocean of this exotic matter, not yet a true singularity. The gravitational pull would be nearly as strong as a black hole's, yet it might still have a turbulent, physical surface. The formation of such an object would be a violent, rare cosmic event, perhaps from the collision of two smaller neutron stars that merge into a single body just heavy enough to fall into the mass gap. The key to finding these phantoms lies in the ripples they create in spacetime. When two black holes merge, their gravitational wave signal is a relatively clean chirp. When two neutron stars collide, the signal is different, often followed by a flash of light as their material explodes outward. A collision involving a mass gap object, however, would produce a unique and telling signature. If a black hole neutron star merged with another neutron star, the event would be cataclysmic. The immense tidal forces from the more massive object could violently tear the neutron star apart before swallowing it. This destructive process would imprint a specific, complex pattern onto the gravitational waves, a signature of matter being stretched and shredded just outside an event horizon. Astronomers are now meticulously listening for these subtle distortions in the data from observatories like LIGO and Virgo. Finding one would be a monumental discovery, forcing us to redraw our cosmic classifications. It would prove that the boundary between a neutron star and a black hole is not a sharp line, but a strange and fuzzy frontier where matter exists in states we have only ever dreamed of. The slow, relentless whisper of Hawking radiation carries a staggering implication, one that unfolds over timescales so vast they defy human comprehension. Every black hole, from the smallest primordial seed to the supermassive giant at the center of our galaxy, is living on borrowed time. For a typical black hole born from a collapsed star with a mass several times that of our Sun, the process of evaporation is almost imperceptibly slow. It would take roughly 10 to the power of 67 years for such an object to fully evaporate. That is a 1 followed by 67 zeros, a duration that makes the current age of the universe seem like a single blink in an endless cosmic lifetime. During almost all of this unimaginable epoch, the black hole would simply shed its mass at an ever-increasing rate, growing smaller and hotter as it does so. The final act, however, is anything but slow. As the black hole shrinks to a microscopic size, its temperature soars to billions of degrees. In its last second of existence, it would release a burst of energy equivalent to the detonation of 1,000,001 megaton hydrogen bombs. This is the black hole's grand finale, a spectacular flash of high-energy radiation and particles that marks the end of its cosmic reign, and then silence. What remains after this explosive death is one of the deepest mysteries in physics. Does the evaporation simply cease, leaving behind nothing but empty space? Or is some tiny, fundamental remnant left behind, a fossil of infinite density that contains all the original information in a near point-like state? The answer would reshape our understanding of reality itself, determining whether information truly is eternal or if even the cosmos eventually forgets. Deep within the heart of a spinning black hole, the singularity itself transforms. The mathematics describing a rotating Kerr black hole reveals a structure far more bizarre than a simple point of infinite density. The crushing weight is shaped not into a dot but into a ring. This ring singularity is a perfect circle of unimaginable density, spinning at a significant fraction of light speed. The consequences of this shape are profound. The equations of general relativity suggest that this ring could act as a gateway. If you were to somehow survive the journey and pass through the center of this spinning ring, you might not be annihilated. Instead, you could find yourself ejected into a completely different region of spacetime, perhaps even a negative universe where time runs backwards. This is not a traversable wormhole in the classic sense, but a feature of the black hole's own warped core, a cosmic carousel with an exit to somewhere truly alien. Yet this strange possibility hinges on a cosmic rule that for now seems unbreakable. The ring singularity, like all singularities in traditional black hole models, is always hidden from our view, cloaked safely behind the veil of the event horizon. But what if that veil could be torn away? This brings us to one of the most speculative and disruptive ideas in theoretical physics, the naked singularity. A naked singularity is precisely what its name implies, a point or ring of infinite density completely exposed to the rest of the universe, with no event horizon to shield it from view. You could, in theory, see it, fly around it, and even study it directly. The problem is that such an object would shatter physics as we know it, the laws of causality, the unbreakable chain of cause and effect that governs our reality would break down at its boundary. The intense gravitational fields would warp time and space to such an extreme that an effect could precede its cause. You could theoretically witness events that have not yet happened or send signals into your own past. The universe would lose its predictability, becoming a chaotic realm where the fundamental rules no longer apply. For this reason, the renowned physicist Roger Penrose proposed the cosmic censorship hypothesis, a conjecture that nature abhors a naked singularity and always ensures it is clothed by an event horizon protecting the sanctity of physics. The search for a violation of this hypothesis is a major pursuit. Some models suggest that if a black hole rotates fast enough or possesses a sufficiently large electric charge, its event horizon could shrink to nothing, leaving the singularity naked for all to see. While we have no confirmed observations, the hunt continues. Finding one would be the ultimate scientific revolution, forcing us to rewrite the textbooks and confront a universe far stranger and far less orderly than we ever believed possible. That exposed singularity, a tear in the fabric of physics, hints at computational chaos. But what if that chaos is not a breakdown of law, but the ultimate expression of it? The black hole might not be a cosmic prison, but a cosmic processor. The way information is scrambled on its surface and slowly leaked back out via Hawking radiation bears a startling resemblance to the most powerful computers we can conceive of, quantum computers. In our own machines, quantum computation relies on qubits, which can exist in multiple states at once. They process information through complex entanglement and superposition, solving problems by exploring countless possibilities simultaneously. A black hole, according to this theory, does the same thing on a cosmic scale. When matter falls in, its information is not merely stored statically. It is violently and chaotically mixed, its quantum states entangled and superposed in an exponentially complex dance across the event horizon. This process is so efficient and so rapid that physicists describe it as the fastest possible scrambler of information in the universe. The event horizon acts like a vast, turbulent memory bank. It's every tiny plank-sized area a potential qubit. The entire black hole becomes a single, monolithic quantum computer, performing calculations of unimaginable complexity simply by existing. The Hawking radiation it emits is not random noise. It is the processed output, the result of this constant internal computation. Each particle of radiation carries away a tiny, encrypted piece of the original information that fell in, the answer to a calculation we cannot yet decipher. This suggests a universe where the most fundamental processes are not just physical, but also deeply informational. The cosmos might not just be made of particles and forces, but of computation itself. Black holes could be the nodal points, the supercomputers of spacetime, crunching the quantum data of reality in their inscrutable depths. What are they calculating? Perhaps they are resolving the fundamental constants of their own internal universes, or processing the quantum data of everything they consume. The idea transforms a black hole from a destructive pit into an active, thinking engine, the universe's most powerful and mysterious mind. This paradox cuts to the very heart of reality, challenging laws we thought were unbreakable. Quantum mechanics, the rulebook for the subatomic world, has one inviolable principle: information must be conserved. Every detail about every particle, its spin, its charge, its history, is a permanent part of the universe. It cannot be erased, only transformed. A burning book turns its information into the specific pattern of smoke and ash. In theory, you could reverse the process, gathering every ash particle and tracing every wisp of smoke to reconstruct the original text. But a black hole presents a terrifying exception. When something crosses the event horizon, it is gone forever, leaving behind only the black hole's mass, charge, and spin. If the black hole then completely evaporates via Hawking radiation, as Stephen Hawking predicted, what happens to the intricate quantum information of everything it ever consumed? According to the classical view, it is permanently erased from our universe. This is the black hole information paradox, a direct conflict between the two pillars of modern physics, general relativity and quantum mechanics. One theory says the information is irrevocably lost. The other says such a loss is fundamentally impossible. This is not just an academic debate. If information can be destroyed, then the entire framework of quantum physics, and by extension, all of chemistry and the predictable nature of reality, is built on a flawed foundation. The quest for a solution has spawned some of the most radical ideas in science. The holographic principle suggests the information is not lost at all, but perfectly encoded on the two-dimensional surface of the event horizon, like a cosmic DVD. The fuzzball theory from string theory proposes the black hole's interior is a tangled mess of strings that inherently stores the data. Another idea is that the information slowly and chaotically leaks out, encrypted within the Hawking radiation itself. Solving this paradox is not merely about understanding black holes. It is the essential key that could finally unlock a unified theory of quantum gravity, a single set of rules that governs everything from the smallest particles to the largest cosmic structures. The fate of information determines the fate of physics itself. The silent, ancient ghosts of the cosmos might be far more numerous than we ever dared to suspect. While we have focused on the giant black holes born from dying stars, an entire unseen population could be drifting through the darkness, remnants of the universe's explosive first moments. These are the primordial black holes, and they are fundamentally different from their stellar cousins. They were not forged in stellar furnaces, but in the extreme, roiling chaos of the early cosmos. In the first fleeting instants after the Big Bang, space was not perfectly smooth. Tiny pockets of incredibly dense energy, fluctuations in the very fabric of reality, could have collapsed directly under their own immense gravity. This process would have sown black holes of almost every conceivable size across the newborn universe, from microscopic specks to objects larger than entire star systems. Their potential abundance is staggering. What if these primordial objects are not rare cosmic fossils, but the most common form of black hole in existence, a hidden multitude weaving through the emptiness between stars? The most compelling role for these ancient relics is as the long-sought dark matter. For decades, we have known that the gravity holding galaxies together is far stronger than the gravity from all the visible stars and gas alone. Something invisible provides the extra pull. We have searched for exotic particles, but perhaps the answer is simpler and more profound. A vast, diffuse swarm of asteroid mass or planet mass primordial black holes, each one drifting unseen through the galactic halo, would perfectly explain the gravitational effects we observe. They would be the universe's hidden architects, their collective gravity providing the invisible scaffolding upon which galaxies were built. This idea goes even further. Not only could they be the dark matter glue, but they might also have been the seeds for galaxy formation itself. In the early universe, a region of space containing a primordial black hole would have had a stronger gravitational pull than its surroundings. This slight over-density would have acted as a cosmic nucleation point, drawing in vast clouds of primordial hydrogen gas. Over billions of years, this accumulating matter would have collapsed to form the first stars, which then gathered into the majestic spiral and elliptical galaxies we see today. Every giant galaxy, including our own Milky Way, might have grown around the gravitational heart of an ancient primordial black hole. The hunt for these invisible giants is one of astronomy's greatest challenges. Scientists use the cosmos itself as a detective tool, employing gravitational microlensing to catch their shadowy passage. When a primordial black hole drifts in front of a distant star, its gravity bends and focuses the starlight, causing the star to temporarily brighten in a specific telltale way. By monitoring millions of stars, we are slowly narrowing the search. Finding them would be a monumental discovery, solving two of cosmology's greatest puzzles at once, and revealing that the true architecture of the cosmos was shaped by the silent, ancient ghosts of creation. The violent death of a star not only forges a black hole but often leaves behind a powerful magnetic legacy. Conventional wisdom suggests the black hole itself should be bald, unable to support its own magnetic field. Yet we observe a stunning contradiction in the form of colossal jets, beams of matter and energy that scream across space at nearly the speed of light. These jets originate from the regions surrounding supermassive black holes stretching for thousands of light years. How can an object defined only by its mass, spin, and charge produce such focused, energetic outflows? The answer lies not in the black hole's void, but in the frenzied storm of matter swirling around it. This is the accretion disk, a vast, flat whirlpool of superheated gas and dust spiraling inward. As this ionized plasma churns at tremendous speeds, its charged particles create immense electrical currents. These currents, in turn, generate monstrous magnetic fields that are twisted and amplified by the disk's ferocious rotation. The black hole acts as a cosmic anchor, its immense gravity providing the energy that fuels this entire dynamo. The most dramatic effect occurs when these magnetic field lines, wound up like cosmic springs, snap and reconfigure in a process known as magnetic reconnection. This launches and collimates the polar jets, funneling material away from the poles at relativistic speeds. It is a cosmic paradox where the ultimate pull of gravity powers the universe's most powerful push. Without these external magnetic fields sculpted by the very matter the black hole consumes, the brilliant jets that illuminate our telescopes would simply not exist. This reveals a black hole not as an isolated pit, but as the heart of an intricate and violent cosmic engine. These magnetic engines reveal a cosmos of violent connections, yet the deepest link of all might be hiding in plain sight within the quantum realm itself. Two concepts that have defined modern physics, general relativity and quantum mechanics, have long been seen as separate languages describing the universe. One paints a picture of smooth, curved spacetime, while the other reveals a fuzzy, probabilistic world. But a breathtakingly elegant idea, known as ER equals EPR, proposes they are not just related, they are two different descriptions of the very same phenomenon. The equation is a shorthand for a profound unification. ER stands for the Einstein-Rosen bridge, the formal name for a wormhole. EPR stands for the Einstein-Podolsky-Rosen paradox, the famous thought experiment that first highlighted the bizarre nature of quantum entanglement. This theory suggests they are one and the same. Imagine two electrons created together becoming quantum entangled. Their fates are linked forever, no matter how far apart they fly. Measure the spin of one, and you instantly know the spin of the other, a connection Einstein famously called spooky action at a distance. The ER equals EPR proposal offers a stunningly simple geometric explanation for this spookiness. What if those two entangled particles are not communicating faster than light through some invisible field? What if they are not separate at all? They could be connected by a microscopic wormhole, a tiny, non-traversable tunnel in the fabric of spacetime. The entanglement is the quantum signature of this minuscule gravitational bridge. You are not looking at two distinct objects sharing information. You are looking at two ends of the same cosmic thread poking out through the spacetime sheet. This single idea has monumental implications. It provides a potential pathway to finally unify gravity with quantum mechanics, the holy grail of physics. Gravity, in this view, might not be a fundamental force, but an emergent property that arises from the complex quantum entanglement of spacetime itself. The vast cosmic web of galaxies held together by gravity could be the large-scale manifestation of an underlying quantum network, a universe stitched together from the inside by countless threads of entanglement. The empty space around you would not be empty at all, but seething with a dense, invisible fabric of these tiny wormhole connections. While these wormholes are far too small for any matter or information to travel through, their existence would redefine our understanding of reality. It suggests that the quantum weirdness of the very small and the gravitational warping of the very large are not just connected, but are ultimately two different faces of a single, deeply interconnected cosmos. Mass, spin, and one other hidden property define a black hole's true nature. Beyond the immense pull of gravity and the dizzying whirl of rotation, these cosmic objects can also carry a third fundamental trait, electric charge. We often overlook this property, yet a charged black hole is a profoundly different beast, warping spacetime in ways that defy our standard intuition. Known formally as a Reissner-Nordström black hole, this object is not defined by a single point of no return. Instead, its electric charge pushes back against gravity, creating not one but two distinct event horizons. The outer horizon behaves much like the one we are familiar with, a boundary beyond which escape is impossible. But inside that shell lies a second, inner horizon. This is a boundary of extreme turbulence, a region where the very fabric of spacetime is predicted to become chaotic and unstable. For a moment, an object falling through the inner horizon might theoretically see the entire future history of the universe flash before it, as light from the outside is focused into a single, blinding instant. How could such an object form? Imagine a star with a powerful net electric charge collapsing at the end of its life, or picture a black hole that feeds exclusively on matter of one charge, perhaps devouring a cloud of protons while repelling electrons. Over eons, this selective diet would build up a tremendous imbalance, charging the black hole like a cosmic battery. The consequences of a significant charge are dramatic. The inner horizon, while fascinating, is also a place of potential catastrophe. Any slight perturbation, a single particle of dust falling in, could cause this fragile boundary to collapse into a true, destructive singularity, wiping out anything that had just crossed. This makes the interior of a charged black hole a fundamentally unpredictable and violent place. The very geometry that allows for its complex structure also contains the seeds of its own instability, a delicate balance between the relentless pull of gravity and the fierce repulsion of electric force. This cosmic dynamo requires a precise mechanism to unlock its staggering power, and the most compelling answer lies in a process named for the theorists who first unraveled it. The Blandford-Zenagic process describes how a spinning black hole can act as a colossal electrical generator, converting its own rotational energy into the raw power that fuels relativistic jets. The entire system begins with the black hole's immense gravitational pull, which drags the surrounding accretion disk into a ferocious, swirling whirlpool of ionized gas. As these charged particles churn at near light speed, they generate immensely powerful magnetic fields that become anchored in the disk itself. But the true magic happens when these magnetic field lines, like cosmic wires, become firmly threaded through the black hole's event horizon. The rotating black hole does not spin these lines passively. It violently twists them, dragging them around at incredible velocities. This motion, akin to spinning the handle of a dynamo, induces a tremendous electrical voltage across the black hole. The black hole effectively becomes a cosmic battery with its poles acting as positive and negative terminals. This voltage is so unimaginably vast that it rips charged particles from the vacuum of space itself, creating a plasma of electrons and positrons. These particles are then accelerated along the magnetic field lines that are stretched taut from the black hole's poles. The field lines act like the barrel of a railgun, funneling and collimating this searing plasma into two narrow, oppositely directed beams. These are the relativistic jets screaming away at nearly the speed of light, carrying with them a significant portion of the black hole's own rotational energy. It is a perfect, self-sustaining cosmic engine. The black hole's spin provides the power, the magnetic fields act as the transmission lines, and the infalling matter in the accretion disk supplies the raw material. Without this elegant process, the most brilliant beacons in the universe, the quasars that outshine entire galaxies, would simply flicker and die. The Blandford-Zenagic process reveals that a black hole is not just a sinkhole for matter, but an active cosmic power plant, its spin slowly being harvested to light up the darkness for millions of light years around. The idea of a cosmos birthing new universes within its black holes leads us to an even grander vision, a multiverse. Our universe, with its specific laws of physics, might be just one branch in an infinite cosmic tree, and black holes could be the buds from which new branches grow. When matter vanishes beyond an event horizon, it may not be traveling to another location in our spacetime. Instead, that point of ultimate collapse could rebound, sparking a new expansion in its own self-contained reality. The black hole in our universe is the gateway, the point of conception for an entirely new cosmos, a baby universe with its own unique physical constants. The matter we see falling in becomes the raw material for an entire new reality, inflating in a direction and a dimension completely separate from our own. In this breathtaking scenario, every black hole is a potential Big Bang event for a fledgling universe. This creates a staggering fractal structure of existence, an eternal cascade where each universe contains the seeds for countless others. This theory even offers an elegant explanation for why our own universe seems so finely tuned for life. The fundamental forces in our cosmos, like the strength of gravity or the mass of an electron, are not random. They could be inherited traits, the unique parameters set by the specific conditions of our parent black hole when it formed in its own, larger universe. In another cosmos born from a different black hole, the laws of physics could be utterly alien, perhaps with gravity so weak that stars never form, or nuclear forces so strong that only hydrogen can exist. We do not live in a special universe, but simply one that is possible, one branch among an infinite number. Black holes, then, are not tombs but cosmic wombs. They are the engines of a perpetual creation cycle, where the end of one story is merely the beginning of another in a different volume of the multiverse. The silent, dark giants orbiting the centers of galaxies are not just consuming matter, they are actively weaving the fabric of a reality far vaster than we ever dreamed. That final, fading hum of a black hole collision is more than just a cosmic chirp. It is a distinct ring, a vibration that reveals the true nature of the new celestial giant just born. When two black holes merge, the resulting single object is not perfectly still. It is born deformed and under immense stress, and it must settle into its final, smooth form. This process creates a very specific set of vibrations in the fabric of spacetime, known as quasi-normal modes. Think of it like striking a bell. A well-made bell does not just make a single, dull clang. It produces a complex chord of sound, a fundamental tone accompanied by higher overtones, all determined by the bell's exact shape, size, and material. A black hole does the same thing, but it rings with gravitational waves instead of sound. The specific frequencies and the rate at which these vibrations fade away are like a cosmic fingerprint, uniquely determined by the black hole's final mass and its spin. By carefully listening to the ringdown with instruments like LIGO and Virgo, scientists can perform a kind of cosmic autopsy. They can measure the properties of this new, invisible object with stunning precision, confirming that it truly is the black hole predicted by Einstein's theory. This is not just confirmation, it is the most stringent test of general relativity ever conducted. The theory makes very precise predictions about how a black hole should ring. If the observed ring-down frequencies were to deviate even slightly from these predictions, it would signal a crack in our understanding of gravity itself. It could be a hint of exotic physics, or even a sign that the object created was not a classic black hole, but something else entirely, like a gravistar. Each new collision we detect adds another data point, another note in the cosmic symphony, allowing us to listen in as these dark giants settle into their final form and prove, once again, that even in the most violent events, the universe obeys a profound and beautiful order. This elegant ring-down of a black hole confirms the universe's deep-seated need for order, a principle that extends to the most chaotic objects imaginable. The cosmic censorship hypothesis proposed by Roger Penrose is a bold conjecture that nature itself enforces this order. It states that every singularity, that point of infinite density, must be hidden from our view, forever cloaked behind the protective veil of an event horizon. A naked singularity, exposed to the rest of the universe, is an abomination that the laws of physics simply will not allow. Why is this cosmic modesty so crucial? It is the bedrock of predictability in our universe. The laws of physics rely on a strict chain of cause and effect. At the boundary of a naked singularity, this chain would shatter. The gravitational forces are so extreme that they would warp time itself into loops, allowing an effect to happen before its cause. You could theoretically witness your own future or send a signal into your own past, creating paradoxes that would unravel the very fabric of reality. Our ability to understand and predict the cosmos depends on this censorship, on nature keeping its most destructive secrets safely locked away. Yet, not all physicists are convinced this rule is absolute. The debate centers on potential counterexamples that could violate the hypothesis. What if a black hole rotates at the absolute maximum speed possible, or accumulates a truly monstrous electric charge? The mathematics of general relativity suggests that under such extreme conditions, the event horizon could shrink to a point and then vanish, like a curtain being drawn back, leaving the singularity naked for the entire universe to see. Other models propose that in the very specific conditions of a collapsing star, a naked singularity could momentarily flicker into existence before an event horizon forms. While we have never observed such an object, the theoretical possibility keeps the debate alive and vibrant. Finding a naked singularity would be the ultimate scientific revolution, a discovery that would force us to rewrite the fundamental rules of reality. It would reveal a universe that is far wilder, far less predictable, and infinitely more strange than the orderly cosmos we currently believe we inhabit. The final theory connects the universe's largest structures to its most mysterious force. At the heart of every galaxy, a supermassive black hole anchors the stars in their great dance. For decades, we have known these giants are there, but their ultimate role in the cosmos may be far grander than we ever suspected. They might be the hidden engines of dark energy, the very force that is tearing the cosmos apart. Dark energy is the name we give to the unknown cause of the universe's accelerating expansion. Everything is flying away from everything else at a rate that is increasing, a phenomenon that defies the pull of gravity. The source of this repulsive force has been one of the greatest puzzles in cosmology. A startling new idea proposes that the answer has been lurking in plain sight within the supermassive black holes themselves. The vacuum of space is not truly empty. It is a seething quantum foam where pairs of virtual particles constantly pop in and out of existence. This process gives the vacuum a fundamental energy. Inside a black hole where space-time is warped beyond recognition, this vacuum energy could be magnified and transformed. The theory suggests that the immense interior of a supermassive black hole is a reservoir for this repulsive energy. As the black hole consumes matter and grows, its internal vacuum energy increases. This energy couples with the fabric of spacetime itself, generating a gravitational repulsion that acts on the universe outside the event horizon. In this view, a black hole is not just a gravitational anchor for its galaxy. It is also a fountain of negative pressure, subtly pushing the cosmos to expand faster. The evidence for this is surprisingly circumstantial yet compelling. Astronomers have noticed a curious coincidence. The amount of dark energy in the universe appears to be proportional to the total volume of space occupied by these supermassive black holes. It is as if the energy needed to drive cosmic acceleration is perfectly contained within them. They are not simply objects within the universe, they are integral components of its evolution, their growth directly feeding the expansion. This transforms our understanding of their cosmic purpose. A supermassive black hole is no longer just a destructive monster, but a necessary part of cosmic equilibrium. Its gravitational pull governs the life and death of stars in its immediate vicinity, while its dark energy heart governs the ultimate fate of the entire cosmos. The largest structures in the universe and its most elusive force may be two sides of the same coin, forever linked in a delicate dance that began with the Big Bang and will end in the final, silent drift of an ever-expanding reality. We have journeyed across the event horizon of knowledge, exploring 25 breathtaking theories that stretch our understanding of reality to its absolute limit. From the faint quantum whisper of Hawking radiation to the holographic encoding of our universe, from the potential gateways of wormholes to the ancient shadows of primordial black holes that may shape the cosmos itself, these ideas represent the very frontier of human curiosity. They are not just wild speculations, but serious scientific endeavors to solve the deepest puzzles of existence, where gravity meets quantum mechanics and information confronts the void. This incredible voyage reveals that black holes are not mere cosmic vacuum cleaners, but the key to unlocking the secrets of everything from the birth of our universe to the nature of time and the possibility of a multiverse. Each theory is a testament to our relentless drive to look into the darkness and ask what is truly out there. The exploration does not end here, however. The conversation continues with you. Which of these 25 theories do you find the most plausible, the one that truly reshapes your view of the cosmos? Let us know in the comments below, share your thoughts and join the discussion. If this journey through the mysteries of space captivated you, be sure to like this video and subscribe for more deep dives into the wonders of the universe.